this. We started with chapter 12. This is test 8, by the way. We have 12.1, 12.2, 12.3, 14.1, 14.2, 14.4. What was chapter 12? Well, let's say sections 12.1 and 12.2. We just took the quiz, obviously, as you remember. What were they generally about? What are the topics we looked at in those sections?
Well, it was about the periods of oscillation and their relationship to the frequency and to the length and the constants and all that. So like 2 pi and L over the square root of L over G, and then 2 pi and then the square root of N over K.
Yeah, so we saw that we were really looking, that was a good explanation of things that were oscillating, and they were analogous to each other. The spring, the mass, was really the same as a pendulum. Now, in section 12.3, we started to look at velocity equals frequency times wavelength, which deviated a little bit from that, but that carried into the next section in 14.1, actually. 12.3 carried right into that. So our first equation that we started with was Hooke's law. Can somebody tell me what Hooke's law states? What does Hooke's law state? No, verbally.
Oh, verbally? The force...
Yes, you do.
required to extend a spring is equivalent to the spring value multiplied by the distance stretched.
Yeah, by the distance stretch, good. So you would say that as you apply more force, the spring stretches more. Or if a string stretches by a small amount, there must be a small force being applied. Or the K value is different. But the idea here is that the amount of stretch in a spring is proportional to the force applied. Okay, they are directly related. As Fs goes up, the actual X value goes up. Okay, and remember that why do we have a negative sign there again? Because the fact that the spring force and the displacement are opposite each other. In this section, we did a lot with theoretical stuff. We talked about a spring mass system that was oscillating back and forth. That would move left to right. Okay, so we have this mass on the end over here, and it was oscillating left to right the whole time. When it was at its extent, when it's fully extended, the spring wanted to pull back. When it was fully compressed, the spring wanted to push out. When it was at rest, in equilibrium, what does it want to do? When it's at rest, in equilibrium, what does the spring want to do? Nothing. Okay, again, 3 states. Either the spring could be stretched. If the spring is stretched and it's all the way out here, the spring force pulls back. If the spring is compressed and it's all the way in here, then the spring pushes back. So depending on the location of the object, the spring either pulls it back in or pushes it back out. It pulls it back in or pushes it back out. When it's in the middle, it's in a state of equilibrium. Now, when the mass gets to the very end, what has to happen? You pull it all the way to stretch, you let go. It starts to do this. At the ends, what has to happen? It has to stop. Again, think about it. If the spring is oscillating back and forth like this all day long, to go from one directional motion to the other direction of motion, it has to freeze at one instant in time. So at the very extremes, the velocity are 0. And in between that, it picks up speed until it reaches equilibrium. And every time it reaches equilibrium, it's at a maximum. Okay, it's at a maximum. What is this analogous to? What is this analogous to? Yeah?
Pendulum?
A pendulum. Can you explain?
Well, the pendulum goes back and forth from its 2 highest points. In the center, it has 0 acceleration. And at both ends, it has 0 velocity.
V equals 0 at the top and the side, or the 2 sides, and it's the top. Because the object has to actually stop. At the bottom middle, it picks up speed, it's all kinetic, it's kinetic and potential, all kinetic at the bottom. So at the bottom is where there's a maximum velocity. Okay, so this is analogous. Recognizing obviously also that at this point in time, gravity is the force pulling it back down. Gravity is the force pulling it. Now remember, gravity pulls down, but what's the direction of motion is at an angle. Okay, so gravity is actually pulling down when it's at some elevation. But which way is it going to move? It's going to move toward that stable point in the middle. This is called a stable point or an equilibrium point, the term we use throughout physics. Equilibrium is right here. Just like equilibrium for the mass, and the spring is right in the center. Centers line up, outer one lines up, outer one lines up. What is the term? What is the term we're using with waves that dictates this angle theta or this stretch x? There's x and there's theta, and they both mean the same thing. What do x and theta mean? What do x and theta mean? There are three terms that we've used: frequency, wavelength, amplitude. Which of those three is theta and x? You got to do your labs, folks. Come on, you did this lab. You turned it in. Theo?
It's amplitude.
Why?
Because amplitude is the height.
Is the what?
Is the height. It's like
Yeah.
the distance. It's measured by an actual distance.
From?
The crest to crest.
Yeah, or
just to
crest to midline. So remember, amplitude for a graph, for a sine wave or a wave, the amplitude is the distance from the maximum to the midline, or the distance from the minimum to the midline, either one. Crest to midline or trough to midline, either way. But the idea here is that this is the amplitude when you pull it up like this. When I let go, and it goes like this and back, what is that called? When I let go and it does this, and we time it, what is that called? When people got to do work, you can't see the same people every time. Come on. You did this in a lab less than a week ago. You let go. You time the time it takes to do that. What is that called? What's the term? The period length. Period length. You need to know these words, guys. You're going to bomb this if you don't. Okay, seriously, a lot of words are involved here. So that's the period length there, the period length. There are a lot of terms we're going to utilize. You need to know what they actually mean. All right. That was 12.2, the idea of 12.2. In 12.2, we also had formulas. The formula here was this. And then the formula here was this, which we just went over on the quiz. Why is it interesting that we look at these two formulas in the same section? Why is it interesting to look at these two formulas in the same section?
Because they're like the same.
Yeah, they're like the same. So the numerator and the radical represents what? For both of them. M and L, what do those represent? Any generic term I can use for those?
I mean, I don't know how to say it, but like for a spring's mass and for that, it's so the
Characteristic, yeah. L and M are some sort of geometric or physical characteristic. Okay? Now, that's of the object or the length of the pendulum. Remember, for a mass spring system, we know it's the mass of the actual mass on the end of the spring that you hang from the spring. For L, for the pendulum, it's the length of the pendulum. L, the length. G and K represent some sort of parameter. K is the spring constant, where G is the gravitational constant. Both K and G are constants. They are both constants. This one has to do with the material of the spring and the spring itself. This has to do with the planet that you're on and the height that you're standing at. But the idea is that these two equations are analogous to one another. The third equation that we wrote down in this section, if you recall, was this. What does that mean? Or this. Same thing, right? What do they mean? What's going on with this one? Joe?
That what's it called?
Which one?
The W.
Omega?
Omega and time, or the period, or if you were, what's the word, like, you can switch them out and it will be the same. Like,
Okay, so if I increase 1,
what?
if you increase this, what happens to this?
It increases.
Yeah, the denominator, they're indirectly related.
Oh, yeah, yeah.
Okay, indirectly related.
Yeah.
Remember, frequency is how many oscillations occur every second. Period is how many seconds it takes for an oscillation to occur. They're inverses of one another. They're reciprocals. Okay, they're reciprocals. It's the term you want to remember. Reciprocals. We talked about waves and energy. We talked about this mainly in part of chapter, I think it was end of 12.3, and then we also talked about it in 14.1. And we talked about graphs. So let's take a look at a quick graph. Okay, you did that in that like simple activity on PhET. And you had to measure the amplitude, the wavelength. You had to see what was a function of. Was the wavelength and frequency related to each other? Was the amplitude related? What did you decipher? What did you come up with from that lab? What conclusions did you draw? So we drew no conclusions from that lab at all? What conclusions did you draw? We have these three parameters: amplitude, frequency, wavelength. We drew conclusions. What were they? Give me one of them at least. People, you got to study. Come on. I know it's 2 days before the exam for you guys, and that sucks. Or more than 2 days, because the other class reviews tomorrow. But you need to study. Can't wait till this weekend just to start cramming. Theo, again.
Is it that they're directly related? They're all directly related. Frequency, amplitude, and
It's not that.
Well, wavelength and frequency are inversely related.
Wavelength and frequency are inversely related for sure.
The amplitude is related to the distance that the spring stretches, or the distance that the pendulum goes.
Okay.
The pendulum.
Was it related to frequency or period at all?
No.
It's not. Remember, an amplitude can change like this. Watch. I could take the amplitude of this wave and double it and keep the wave the same. And it would still have the same wavelength. The length is literally, right? The length is literally from here to here. That's one wavelength from there to there. The wavelength didn't change and the amplitude doubled. It does not have an effect on it. Joe.
Wait, but what if both the yellow and the white line both have the same amplitude? Does it didn't change? It has the same like displacement.
That's wavelength. That's
Yeah,
wavelength.
it's the same.
This is amplitude. Okay? So I said I'm doubling the amplitude, yet the wavelength is the same. All right? Again, this is wavelength. This is amplitude. That's why in the lab, when you did it with that PhET lab, you put a ruler up. The ruler was used vertically to measure amplitude and horizontally to measure wavelength. Okay? Those two parameters. Now, we went on in chapter 14 to not only talk about this continuously, but we also talked about equation, the following. We used that equation right there. And in this equation, we recognized that if the speed of something is held constant, so let's say it's 10 meters per second, if I increase frequency, I have to decrease wavelength, or vice versa, which again tells us how wavelength and frequency are inversely related. What if this was an electromagnetic radiation? What do you know about EM waves? Think back to the last two lessons we did. What assumption can you make if I tell you that it's electromagnetic radiation that's causing this? What assumption can you make?
Has a high frequency?
I mean, it might, but that's not an assumption we can make. Ellie?
Isn't it that with aren't they like directly related? Or like-
They are indirectly related, yes. These two things are indirectly related. But what was the thing that we could make an assumption of, or we could say?
That if one was up, it goes down.
Yeah, absolutely, you're 100% right. But beyond that idea, there was another thing we talked about with EM waves specifically. Electromagnetic radiation. What was it? You need to know this because I'm not going to tell you on the test.
Well, they have things oscillating magnetic, like oscillating electric and
Magnetic fields. That is true, but specifically for this equation I'm asking, guys. I could ask you the following, and maybe you could figure it out based on this question. I could say the wavelength of a radio wave is 1.2 meters. Determine its frequency. How could you do that with this equation? I'm only giving you the wavelength, that's it. I'm telling you the wavelength is 1.2 meters. Determine its frequency. How could you possibly do it, Emma?
Minus 3 times the
What is that thing? Whenever you have a problem involving EM waves, the velocity is 3 times 10 to the 8. It's a given. It's on your formula sheet. C equals 3 times 10 to the 8. So this equation, if you want to write it this way, you could write it as C equals omega lambda for EM waves. C is the speed of light. Omega is frequency. Lambda is wavelength. Lambda. Like a lamb, another word, duh. Lambda. Okay, it's a Greek symbol.
A lot of Greek in physics and math.
Absolutely, a whole lot. Absolutely. Why is that?
Because they invented it.
No.
They studied it, huh?
Yeah, I mean, they came up with a lot of the theorems.
Yes, that's true, they did, but why else? Come on, why else?
They focused on it? Like, did
that was the other famous mathematician.
mathematician, like, Aristotle?
How many letters are in the alphabet?
Not enough.
Thank you. That's the answer. Yeah. Not enough, okay? There's only...
Oh, this year,
Nothing, no, we're not gonna keep stop.
I'm just kidding. How many days are in February?
Besides,
This year, 29.
In normal
Okay, okay.
28.
Perfect.
Okay.
Normal people don't know this.
What?
For our math test. I didn't know that either. I didn't know it either.
That is common knowledge.
I'm gonna learn. No, it's not. Who's supposed to tell me that?
How did you never...
I never learned.
you don't learn it though, you just, I feel like
Decided that.
No one ever told me one.
If you polled like 100 people, I guarantee you 90 would know it. 90 would know it.
No.
we went around the comments, we went around the comments.
23 people said they didn't know, and 21, you're the 21.
21st?
Let's give a question.
I don't know, that's like saying like, you should know how many cards are in a deck of cards.
52. Yeah, but the thing is that he told us that in class. He never told us how many days.
But I feel
If he did, I was never told in my
So did you ask during class?
You don't ask if you like laugh.
Sean didn't know either.
Got mad and roasted.
That's alright, it's alright. Well, hopefully you guessed 28 or 29. And you...
I guess
Alright. Yeah, let's get back to physics. Back to physics.
Go further.
No further. We also talked about the fact that a wave's amplitude dictates how much energy that wave carries. Okay, how much energy the wave carries. So we know that if, for example, we double the amplitude, what happens to the amount of energy carried?
Wait, amplitude and energy? Oh, if we double the amplitude, the energy also is going to double. Well, maybe not double, but it'll increase.
It'll increase. Why?
Because E is equals to like A squared.
There it is. It's proportional to. Yep. Proportional to. So the energy carried by a wave is proportional to the wave to the amplitude of that wave. So if you triple the amplitude, you're raising the energy by 9. Okay, by 9. An amplitude of a wave that gets higher by a factor of 3 carries 9 times as much energy. And this is logical also, guys. It's very logical. I gave the example in class. Do you remember the example I gave? What was the example I gave in class to demonstrate this?
Throwing a pebble in a pond and then throwing a big rock in a pond.
Yeah, very simple. Throw a pebble in a pond and throw a big boulder in a pond. A lot more energy in the boulder, the amplitude goes up by a giant amount. Now, I'm telling you that it's proportional to the square of the amplitude specifically here. There was another relationship we came up with light and luminosity and brightness. And we said the brightness that you see is really the actual brightness of the bulb over the change in length squared, or the factor of the change in length squared. So here's what this means, right? If I have a bulb and it's right up against my eye, well, besides getting some retinal damage, I'm going to see it at a certain brightness level. And then maybe I double the distance from my eye, or triple the distance, it goes down by a factor of 9. If I quintuple, if I take the distance and multiply it by 5, so let's say that the bulb is 2 centimeters from my eye, and then it's 10 centimeters from my eye. To go from 2 to 10, multiply by 5, you'd put a 5 here, which means the brightness would go down by a factor of 25. So the factor of increase in the distance from the source is indirectly related to the brightness you're going to see. Okay, so again, I double the distance away from the light, my brightness goes down by a factor of 4. Triple the distance from the light source, the brightness goes down by a factor of 9. Okay, these are very similar, by the way. You see the square term, but clearly one is in a denominator and one is in a numerator up here. Let's see. We talked about waves. We talked about transverse, longitudinal, pulse, periodic. What do those terms mean? Pulse versus periodic. Pulse versus periodic. Hey, look at it right now. What kind of wave is that outside? Pulse or periodic?
Periodic.
Why?
Because it's going on repeatedly.
Yeah, it's really annoying the hell out of me and it keeps going on repeatedly. Okay, it's periodic. But a single sound wave coming out of the ambulance would be a pulse wave.
And
It's a
so
hump.
with multiple
Like a
pulses,
hump, yes.
with multiple pulses make a periodic.
That's exactly right. Okay? Multiple pulses is a periodic because the source continues to repeat itself. The source of the wave repeats itself over and over and over and over again. Transverse versus longitudinal. Yawning is very contagious. Transverse versus longitudinal.
Transverse, it travels left to right, and then it moves up and down.
Yeah, so the wave would be oscillating like this while moving left to right. That would be the idea of a transverse wave. What about a longitudinal wave? It's going to move left to right, but which way is it going to vibrate?
Left to right also.
It's also going to do it, so it's going to look like this. I know it's hard to see this. Okay, it's not moving up and down. So imagine this. This is transverse. I can show my hand a lot better. This is longitudinal. It's vibrating left to right while moving left to right. Think back to the slinky. When we sent the transverse wave back and forth, you saw me, or whoever I was synced up with, I think it was Frank, I forget, doing this.
Yeah.
Okay, and it made a transverse wave. But when we went like this, we sent a pulse like that, it vibrated in the same direction the wave was moving, which made it a longitudinal wave.
How do you spell that?
Longitudinal.
So the top one, wait, which one's longitudinal is the top one?
No, the longitudinal is bottom.
Okay. Remember, the word transversal makes you think of two parallel lines and a transversal cutting through it. So think of this as the vibration moving up and down, which is cutting through the direction of motion. The direction of motion is left to right, the vibration is up and down. It's like a transversal going through the parallel lines. That's what the top one makes you think of. The bottom one, though, longitudinal, think of say latitude, longitude, don't think of it. Just confuse you more. Okay, but again, this wave is oscillating up and down. That's like a transversal cutting up and down through two parallel lines. Transverse. What else? We talked about colors. We talked about how colors work. We talked about polarization. This was all yesterday, right? The idea of colors is that the color you see is what? Is the reflection of that color. What's happening to all the other colors?
The absorption of the being absorbed.
By what?
The absorbing
By the material that's.
Yeah, the material on the surface. Okay, the sun is giving off the light rays, giving off, and black, the color, is the absorption of all the colors of the spectrum. White light is the reflection of all the colors of the spectrum. Okay?
So,
Yeah.
just curious, let's say like you're looking at a light bulb, right?
Mm-hmm.
So the point of origin of the light, right, is in the light bulb. So in theory, though, that does look white, right? Like
Mhm.
that is its point of origin, even though obviously like everything else that gets absorbed, I guess that's light we're talking about.
I don't know what your question is. No.
Right. So like in theory, right, like a surface is the reflection of all materials, right?
Of all the light.
Of all light, right?
Mhm.
So if the point of if light, so like if I'm looking at any color, that means for any other color. So the light bulb, inside the light bulb, or the light bulb itself, comes to me as white. So
It means
that
you're seeing
reflecting
all the
off of
colors.
something?
No. It just means you're seeing all the colors at once, which produces white light. Yeah, it's not reflecting because it's a generation, right? That's generating the light. When reflections, you're talking about the light's already been generated somewhere else and it's being reflected off a
Right.
surface.
So that like so the inside of these is white, but this is not white.
Correct, because this is absorbing all of the colors of that white
And
light.
that's the compilation of the molecules in the material, or how does that? Why is this black?
It's a really good question. It has to really do with the frequency of the wavelengths of each color. So red, if you recall, let me get this right. Red had lower frequency, violet had higher frequency. So the frequencies of the waves indicate what can actually be absorbed by it. So when you have changed frequencies, remember frequency is how many oscillations occur. So like this would be low frequency compared to this, which would be a higher frequency. So the different colors oscillate at different frequency levels. So one of these could be absorbed by one surface while the other would be absorbed by another based on the actual material itself that the surface is made up of. I don't know on the molecular level. That's a good question, what actually happens. That would be something that maybe Mr. Joseph could answer, or we could look up in material science. That's what that would be. Material science under that topic. Benno, maybe you could research it for us and figure it out. What else? That's kind of everything that we talked about. What questions do you have for me? What questions do you have for me? What do you want to look at? What do you want to work on? Got about 6 minutes. What do you want to work on? Anna,
What kind of problems are going to be like asked? Because that sounds like weird. Like,
what do you mean?
Oh,
we just
was there
said
any-
practice. We just said practice problems
Do you mean math or conceptual or
and
what?
conceptual.
Conceptual.
Yeah.
Conceptual.
So conceptual, you can imagine problems that ask things. Remember the beginning, the first slide that we went over with the spring and the pendulum oscillating? Come from there. Conceptual will definitely come from chapter 14, a good amount. Conceptual will come from the ideas like, your amplitude has no effect on the frequency, or your frequency and your period are inversely related, or if I double the length of a pendulum, what happens to the period? Those would be their conceptual ideas. Okay? The mathematical stuff you could expect, we really only did a few different formulas. Really pretty much expect all of chapter 12 to be mathematical. Okay? Also conceptual, but what I'm saying is there's not going to be much mathematical from chapter 14. You could expect Hooke's law to come up mathematically. You could expect tau equals 1 over omega to be mathematical and conceptual both. And you could expect these two formulas. The only other formula we talked about was this, and it was in chapter 12, section 3, and it was also that was section 3 of chapter 12, and then you could replace it with C, and that was in chapter 14. But the conceptual stuff in this chapter has to do with things like, when we've talked about oscillations, we've talked about the analogous nature of those two. We've talked about what happens to a spring when it's fully extended. Well, it's got no velocity, the force is pulling back. Talked about light just now, the ideas of light, the colors of light, what they mean, how they're used. And that's really it for conceptual. There wasn't like too much to talk about there. I'm trying to think of other stuff that we're forgetting. Understanding the difference between transverse, longitudinal, periodic pulse. That's all conceptual for sure. Energy and amplitude, that relationship is really conceptual. That the more the amplitude is, the more energy you're using. The ideas of electromagnetic radiation and their applications could be useful. So for example, like an application of gamma rays, maybe for cancer treatment. How is that actually used? Or infrared waves, how are those used? Well, those are used for thermal imagery. So maybe, infrared goggles or binoculars for the military. So we went over a lot of applications I talked about. Be able to name them and also explain how they're used and how they make sense. Obviously, if I ask for an example of microwaves, you cannot give me a microwave. Okay? And I'll put that in directions if I specify that. But please don't answer for radio waves, radios. Yeah, yeah.
What would be an example?
Yeah.
Of microwaves?
Yeah, microwave.
What was something we talked about for microwaves? Radar we talked about for microwaves. Radar is used. I think we only talked about physically a microwave and then radar systems. That was it for microwaves.
Then what
And then what about
radio
radio
waves?
waves? Is that like cell phones?
So radio waves for any general communication from towers. You can use radio waves. Walkie-talkies use radio waves. For antennas, any antennas that are used, either they're on TVs or anything else, on a radio itself. Satellite dishes use radio waves. Yeah, on.
Sorry, I just like wrote down a list. Wait, which one for gamma rays and infrared?
For gamma? These are all in your notes, guys. They're all
No,
there.
I know, I'm just putting in like.
I'm just literally telling you what's in your notes. Gamma was for irradiation of food, to get rid of radiation. For testing, for structural analysis, if there's like a crack in a beam. For cancer treatment. Infrared was stuff like thermal imagery. Like a remote control for a TV we talked about. But explaining physically what's happening for those. Understanding the idea that the EM spectrum is really comprised of many mini spectra, I guess. And each of those spectrum values or lengths corresponds to frequencies and wavelengths. Understanding that radio waves have high wavelength and it gets lower as you go down the chart. And God bless you. And vice versa for the frequencies there. Other questions you have? Other questions? Definitely expect questions of level of difficulty for the math part that was on your quiz. That's reasonable. Your homework questions that involve math. The problem set that's due tomorrow that involves math. Remember that it's due when tomorrow? At noon, please. Get it before noon. Please don't dilly-dally and tell me, couldn't get on Wi-Fi at 11:55. Sucks to be you. Get it before then.
Will there be more conceptual on this test than math or more math?
Yeah, I'd say that like a third of it will be math, the other 2/3 will be conceptual. There's not too much math that we did, so.
So how much of the conceptual stuff will be waves? Pretty much all of it, right?
A lot of it will have to do with waves, yeah. Because I mean, everything we've studied in these two chapters has to do with oscillations and waves. But there's also conceptual things about Hooke's law. Remember Hooke's law? Fs equals negative kx, that idea? That's definitely conceptual as well. I mean, mathematical in addition, but also conceptual.
Will we have to explain any of the formulas, or is that secret?
I mean, you should definitely be able to explain the significance of the following. Like, for example, look, here, why is the period directly related to the mass? If you have more mass, the spring is going to get pulled down further, it's going to oscillate longer, so you have a higher period length. Why is it indirectly related to K? K is the stiffness. If the spring is stiffer, it doesn't move and oscillate as much. So a lower period as a result. So you're going to be able to see these relationships. Why is the length directly related to the period? Longer the pendulum is, the more arc it has to cover, it takes longer. Why does it not involve mass? Why is the period of a pendulum not involve mass at all? Why is that? Who remembers?
Is it because it doesn't matter?
Yeah, remember we talked about how it like cancels out? We talked about how at the top you have mgh, at the bottom you have 1/2 mv squared. Okay, please study. You need to do well on this test. The last test was not a positive test as a whole. Okay, we need to see some better grades.